So, good morning. So we continue our study of the Ising model. Okay, in the mean field approach. Okay. And so we earlier lectures we had taken B to be non-zero, and so now so we are now studying the effect of turning on a magnetic field. Okay, so this is what we did last time, and so for T greater than Tc, which we know in the absence of a magnetic field, it's a paramagnetic thing. And so if you turn on a B, like any paramagnet, there will be a magnetization and the solution is unique. Okay, so we had no issues. So you get unique solution for M, the average magnetization. Okay, so I sort of showed you. I drew this picture towards the end of last lecture, and so the point is that when you apply large enough B, so T less than Tc, we know that even when there is no magnetic field, there will be magnetization, and there are two possibilities. We know that, and that's the ones which are marked here. Okay, so we also know that for large positive B, it'll all the spins will line up and it will saturate, and the average magnetization will be plus half. Same thing for large negative B, which is at this extreme, it will saturate to minus half. Okay, but we know, so if you just naively extrapolate what I've shown with dotted lines, last lecture I drew properly, so that if you start from a large B and go this way, obviously, and that means you'll have some residual magnetization, which is some positive number. Then what will happen is if you further reduce, you will go along this dotted line. Okay, but if you but these will be what I was telling you are metastable. Okay, and the key point here is that there's a discontinuity in M. Okay, so if you just focus, let's say we are doing stability, and then we look at this thing. Then so the idea is that if it's metastable, if you wait long enough, it will go to a stable ground state, and that stable ground state for these points are these lines, which are indicated with this thing. Okay, so is this clear? This picture? I'm not proving stability, metastable, etc. But we'll see how to get to that. We may not dot every I and cross every T, but maybe I'll put that in an assignment. Okay. So any questions regarding this picture, because this is an important picture. Is this okay? Everything is clear about this picture? Okay. So actually I have an exercise. Yeah, go ahead. No. I'll explain symmetry breaking again. Yeah. So, okay. So, symmetry breaking has to do with a choice of one minimum. Okay. So, yeah, we'll see that. We'll discuss symmetry breaking. I haven't defined it properly. I will define it probably in today's lecture. Okay. So the dark lines are all stable. Okay. So, so the thing is, so actually, a numerical exercise for you. Okay, so reproduce these curves by numerically solving for m as a function of b, keeping t less than tc. Okay, so we had that function, right? M equal to m equal to tan hyperbolic, I guess tc upon t times 2m plus some factor times b. This is the equation we have to solve, and of course we have to pick the different roots, and with tc by t being greater than 1. Okay, so that is the thing. So you have to solve. You won't solve a continuum set of points, but you can solve some discrete things and plot them. Okay, so please do that. So it's just a nice numerical exercise which you can do. Okay, so so the most important feature is that what is that? Yeah, is that m is discontinuous now as a function of b. Okay, so it goes. So you can see if you look at it at b equals, so you get different values. For b tending to 0 from the plus direction and b tending to 0 from the minus direction. Okay, so if you're coming from this direction, you will come to this point, and if you come from this direction, so you see that there is a discontinuity. Okay, is this clear? Okay, so so now so what I want to say here is that this says that so the transition. Uh, I don't want to say anything about the transition. So, but I just want to ask, how do we, so understanding the stability. Of the solutions. This is something we didn't do. I just have been stating. So I'll show you what I have in mind. And so the idea. So let's first do b equal to 0 and then turn on. Okay, for simplicity. And of course we will put it back on. Okay, so the equation then is 2m equal to tan hyperbolic of okay. So and then so when we wanted to get some explicit solutions, so at least we can expand this to okay. So let us just truncate. So let us truncate to third order. Okay, so that we already have done in some sense. So then we will get So the equation becomes now 2m into 1 minus dc upon t into 2m plus 1/3 dc upon t into 2m equal to 0. Okay, so this was the equation, and we have three solutions to this. But what I want to say is, let us look. Okay, so let the above equation. Yeah, what? Yeah, thanks. Thank you. Okay, so let the above equation arise as the extremum of a potential of a function or a potential. I'll call it f of 2m. Okay, so that means, so let's call this star. So df by d of 2m or m equal to 0 implies star. Okay, so what is this f of 2m? So okay, so that's what is the thing. But how do we figure that out? We know the equation df by 2m. So we just, what is it we have to do to determine f? Huh? Hello? We have to just integrate. Nothing fancy, right? So we just integrate. So okay, and I put 2m in. Okay, so let's call the variable x now. So x equal to 2m. So then you will see, and let's just do some uh, multiplications so that I get this term becomes x cubed or whatever. So this will become. I'll rewrite this equation. Give me a second. So I'll write this equation as yeah, 2m whole cubed plus 3 into so that's tc by t whole square, right? So it becomes t by tc whole square into and let's okay. So close to, in some sense, close to tc. Actually, we can even forget. We can think of this as being uh, 1 if you want. Okay, because there will be some higher order corrections to that. So the operative term here is that this term is a positive number for t less than tc. Then I put out a minus sign. Okay. So f of n, f of x by integrating this will be x power 4 by 4 minus this whole thing. So I'll put a proportionality constant because I will want to multiply. I have the freedom of multiplying it by some other constant just to make it look nice. Okay, I don't know what that is. 2m whole square by 2. So x square by 2 plus constant plus some constant. Is this okay? What I've done? Okay. So now we can rewrite this object. So I have the freedom in writing this constant. What is this constant? So I will write it in a particular way. I will write that as x square. Okay. Uh, minus. So I'll put a 1 by 4 here. Okay. So that will be 12 here. So I'll get 6. F of x is proportional to this quantity. 1/4, I pulled out a 1/4. Okay, do you see this? So I've done completing squares in some sense. So I said I will add a constant such that this becomes a perfect square. And this is what you get. So you get x power 4, the x square coefficient will match, and then there'll be some constant. I don't worry about that. Is this fine? Okay. So, so if you look at this thing, so this equation I can rewrite. So I can write it going back to the original variables. Is that f of 2m, okay, is proportional to 2m whole square minus 2m naught square whole square, where I'll define m naught, 2m naught, to be this constant, this object. 6 into t by tc whole square into 1 minus t by tc. Okay. So the reason to do this is, yeah, thank you. I think I should write under. Okay, so now that we have everything set here, we let us plot f of 2m now, this function. Okay, so first thing is, you see it's a perfect square, so it's a positive number. Okay, it's always positive, and the minimum values occur only when I'm okay. So before that, so it's a perfect square. Okay, implies f of 2m is always greater than or equal to 0. Okay, so minimum, true minimum, is when it is 0. Okay, this occurs when okay, yeah, 2m equal to plus or minus 2m naught. Okay, is this clear? Okay, so if you just go ahead and do the plot of this function, which I will do right now, and you will find that it also has a maximum, and the maximum is at 0. Again, that's very easy. So, the positive function. Very good. So tick points. So 2m naught symmetrically. So this is 2m versus f of 2m. F is going to no need to write f of 2m. Okay, so this function, and what is the value at 0? It is just this m equal to 0. If you put here, you get, so it's like 2m naught power 4. Okay, up to some overall proportionality constant. Okay, so just that sort of a thing. So this will work. So this will have, let me draw some things and connect. The minimum here, and okay, so now you can see that the three solutions, so the three extrema of f of m or 2m is at 2m equal to 0 plus or minus 2m naught. Okay. However, from this also, with this picture, you can, so stability in the sense of this, you can see that if we are going to minimize f, okay, so f is some kind of a free energy from a thermodynamic viewpoint. This okay, so this kind of picture will capture the whole story. Okay, that there are three minima, and you can see that this is unstable, and these are stable. Okay, is this clear? Okay, so now we are ready to ask, and so you remember there were three solutions which we saw earlier. So we're just writing some free energy, and so maybe we can ask, can we derive this from some kind of first principles? Possibly yes. I don't know. Okay. Okay. So but I'm just writing something which will give you this equation that we got. Okay, we truncated. But now one more point you would ask, okay, so but we did a truncation, but what if we had the full equation? But one thing we know is that the full equation nevertheless had the same, it had three solutions. Okay, so the general picture, even if you do take the full nonlinearity into account, will still look like this. The value, precise value of m naught will be not what we got here. So I've already taken care of that by saying, okay, I wrote 2m naught equal to this, but this is only true for t close to tc, close to tc minus from the lower side, right? That's what we know. Okay, and so yeah, one more feature which we can see out here is that this height here for what is this height? We just saw that that was proportional to 2m naught power 4, which is proportional to, okay, so this height, okay, is goes like 1 minus t by tc whole square, because m naught goes like square root of that thing, so you take its fourth power. So you can see that as that is one thing we see. Then as t approaches tc from below, okay, we see the height. We see that the height, okay, of well, you understand what I'm saying, right? The height of the value at m equal to 0 goes to 0. Okay, and of course we also know that the m naught also 2m naught also tends to 0. Okay, so what we have is so you just dynamically think of changing, taking t to tc. So what happens? First thing is that these two guys will move closer to 0, and this height will come down. These three things will happen. So that at precisely at t equal to tc, it will just become m not become 0. So it will just become, so at t equal to tc, f of m or f of x is proportional to x power 4. Is this clear? And how does that, if you plot that function, it just looks like it has a nice single minimum. Okay, so this is what is happening. So the general setup is that this is at t equal to t greater than or equal to tc, it will look something like this, and at t less than tc, you get this here. Okay. Actually, I shouldn't. I should just say, yeah, good point. I was also wondering if I should make that. Need not. It's actually 0. That's it. Okay. Okay. So this is the scenario. So now what we want to do. So okay, b not equal to do 2. above picture. Okay, and again it's useful to just work in the regime t equal to near t equal to tc uh, and look at the and work to cubic order and see what are the kind of terms that we get in that equation. Okay, so we know the formula. So the consistency condition and what is the factor with b? Does anybody know? It's plus b, beta b. Okay. Okay. So this is the equation that we need to solve. And like before, we'll just expand this. This okay. Is this clear? Hello? This is just a power series. Yeah, yeah. So now from this, so the idea is that what we want to do is we would like to infer the kind of changes, kind of terms that appear in f of m, f of x due to b. It's clear, right? I can do the same thing. I can truncate. I will just truncate. Okay, and then I will look at terms. So first thing, yeah. Okay. So you see here that so coming back to this f of m, this f of m had a symmetry. Where is f of m? Here. Under m goes to minus m because it's a function of m. It's an even function of x. Okay. So okay, that means f of x is equal to f of minus x. Okay, and okay, and this is a if you do it two times, okay, this is actually a symmetry of the system. Okay, which is the Z2 symmetry. It takes all the sigma i's. If you take them to minus sigma I, you go back and look at the Hamiltonian. Okay, and this implies that m goes to minus m. Right? X is like 2n, so x going to minus x. Is this clear? So this is a symmetry of the system. That means it's a symmetry of the Hamiltonian, for instance. Okay, and also it shows up as a symmetry of the free energy. Is this clear? There is no so this is a discrete symmetry, and Noether's theorem, which says that for every continuous conserved quantity, there is a conserved current. Discrete symmetry do not have conserved quantity, so Noether's theorem is not applicable here. Okay, so yeah, discrete means it's a number of group elements is finite. It's a finite group. So in this case, it's a two-element group, right? G, you apply square is identity, so it's Z2. But rotation, right? So there is something called an infinitesimal rotation. Is there an infinitesimal element which you can construct for this group? You can't, right? Either you invert or you don't. That's it. Yeah, it's digital, so it is discrete in that sense. Okay. So yeah, so remark is know this theorem which connects continuous. So there should be some Lie group, continuous symmetries. Currents is not. Okay. So there is no conserved current, nothing. Okay. So first thing we will observe. So for is so we will see that f of x is no longer even when p is non-zero. Okay. So if you think of f of x as some power series, okay, so f of x, okay, originally we had x power 4 plus x square with some terms plus maybe constant, okay, but now we will get terms which will depend on b also, okay, but now there will be x cubed new terms, x also, so these are new terms which appear. Okay, so now we can see, right, if you do df by dx, x cubed guy will come, means there will be a term which will be proportional to x square in the equation, and the other one, the second, if you take derivatives of this with respect to x, you get a constant. So there should be constant pieces, and this thing is the equation which we are solving, and let's come back to this and look at this equation. Okay, so this is the equation. And you see here that what was originally just 2m cubed now is some 2m up to some factors plus this thing. Okay, so now we will see that there is a term, so in the, which is, so if you take the thing where you square this and this thing, so you see that you get a 2m square term from this, expanding this binomially. You also get a term where this will be 1 power, and okay, so and you'll also get a constant piece which will come completely from here. Okay, there's also a constant piece coming here. Okay, so this is what is happening. Okay, so let's just try to isolate. Okay, so let us work out these terms. Okay, so I'm sorry, I need to write those equations again. So the equation, so 2m into 1 minus tc by t. Okay, then minus b. Once again, I wrote b and but forgot these two terms, beta b. Plus 1/3. Right, so this is the equation, and we need to this thing. So again, like before, what did I do? I multiplied it by 3 into t by tc whole cubed. So then I'll get some terms. So I'll do that here. 2m into, as before, t by tc whole square there's a minus here, 1 minus t by tc, after we take that, plus, so now I have to multiply this, and write it as t by tc whole cubed, whole square, and beta is a 1 by kbt, so there will be some cancellation, so we'll get, what will we get? So t, yeah. Oh, there's a 3 also, right? Okay, this is what we get. So now we can do the integrations if you wish. If you do the integration, okay, so yeah, cube, but I took in a t by tc multiplied here into this term. We multiplied by 1 power of t by tc, so I flipped it to t by tc, and there's a minus sign which comes, which I put here. It is there, and same thing I did here also. I multiplied this, so beta is 1 by sorry. Okay, 1 power I've used up. So actually, a temptation for me is to put this t by tc whole square to 1. Okay, that really is not a big deal. Okay, so what we can do now is we just integrate these things, right? So you can just integrate this, and this will give you a square term. But what I want to say, so we can, yeah. So let's do that. So integrate. So and that will be f of n equal to what proportional to this thing and to. Okay, integration of a constant plus, now I have to integrate this, so that will just be 2m plus t by tc whole square b by 2, sorry I have to, it's not so hard but it's a little messy, power 4 by 4 equal to c. Okay, so so you look here, so let's look at the focus on the so there is, so f of 2m or f of x is equal to x power 4 by 4. So I'm just focusing on this. So it's x power 4. There's a 1/4 which I pull out, and I just want to focus on this term. Okay, so now you expand this, so you get a term which now has 3x cubed, and the coefficient is this guy. There are other terms, but this is what we get. Okay. There's also, are there any other, so there are also terms, so we have to actually do a little bit more work. So there's also a term proportional to x, okay, and x square. So I won't look at that, but I just want to look at, for now, for looking at this x cubed. So what we want to see is that the x cubed term, coefficient of x cubed is proportional to b. Okay, so clearly, I mean, like all the extra, especially the cubic and the linear terms which come, they should go to 0 as b goes to 0, and that you can check. So this is one linear piece, but there'll be a second linear piece coming when you expand this guy also. Okay, so but let's just focus on for simplicity, I'm just looking at only the cubic piece, but the general conclusion will not change if you put everything, and that's part of your assignment. Okay, so this is what we get. So now let us plot. So let's take b greater than 0. It's not just non-zero. Okay, and look at this. So the f of x, the cubic term, is has coefficient. Which is greater than 0. Okay, so if you plot just the cubic part, so if you have a function, cubic function, so some ax cubed versus x, so that has this behavior. Right? What does it do? It pushes. Okay, so this is positive and negative for. Right? So now, so instead of now drawing all these things, if you go back to the picture, so let's go back to this picture here, and so yeah, so we are at t less than tc, and these two are degenerate minimum. So what is happening is we're adding stuff here, which will push it up, and it will push something down on this side. Okay, so adding this cubic term to. See, there might be terms which might shift, shift sideways shift. I'm looking more in terms of what it will do to the magnitude. Okay, adding this cubic term to f of m when b is 0 to the f of m that we got when b was 0, we see that the minimum at 2m equal to 2m naught is pushed up. The value of the. Okay, and it is pushed down at 2m equal to minus 2m naught. So what does this mean? It's not symmetric anymore. Yeah. Okay. So implies that one of the minima is only a local one. Yeah, only a local minimum. And the other is a global minimum. And you can see that if I change the sign of b, okay, this will flip sign. When b goes to minus b, this will flip sign. Right? So then the what was global in one situation will become local in the other, and the other way around. Okay? So we get two pictures now. So I draw only one. So at least initially this will happen. And yeah, so so this is the thing. So this will be so this is an example of a metastable. Okay, metastable minimum, because there is something lower. Of course, quite generally there is a barrier. So you'll have to wait. So, but in thermodynamics, you wait long enough for a system to reach equilibrium. So if you're waiting here, and then thermal fluctuations can take it from here to here. Okay, so it has to jump over this barrier, but thermal fluctuations, if you can do that, and so that is what happens. And so we need to go back, and so this was the scenario that I was sketching earlier, where I said, what did I say? I said that in the beginning of the lecture, I draw this picture. Okay, so that we started out, and we had something like this, and then this became metastable. So we have to check what is happening. Okay, here B is positive. Remember, B is positive, and so what happened was that this is the 2m equal to 2m naught solution, plus 2m naught solution, and when you had a positive B, that solution got lifted, right? That got pushed up, and so this is metastable. So what we saw, I've only done it with the cubic term. Okay, you can argue so we should argue that the other terms don't affect this conclusion. Okay, so is this clear that this was the guy 2m equal to m naught? So this was for, okay, so this is, so here we are starting from b greater than 0. So this is what is relevant to what we look in our analysis, that is this guy. Okay, so is this clear? So that's why I call this metastable. Okay, so but the true minimum here is this fellow, or things along this part of the curve. Okay, so I'll just conclude here. So exercise. See that the other terms are consistent. With our conclusion that for b greater than 0, okay, so for our conclusion that for b greater than 0, the one of the solutions is not a global minimum. Okay, so yeah, so one more point here is that yeah, so we need to assume okay, so this is important. That means we are in this neighborhood. Okay, so we are close to, so because if b is large and positive, we know what happens. It will again become stable. Okay, so we have to check so this picture which I have drawn is correct, but so this is something which you have to check. Okay, so this will be maybe part of your assignment, but I'll just stop here. Okay, so what I try to tell you is that we can construct this function whose minima are actually your values, and you are solving it, and you get multiple solutions, and these are of course in general a function of t and b, and so you can study how it changes for various things. So we did it in different regimes, which was t less than tc, t greater than tc, so on and so forth, and we handle these things. Okay, so so this gives you some insight into how stability comes. in this setup. Okay, so but in some sense you can say this function seemed a little ad hoc. Okay, it is, but probably we should be able to relate it to some free energy in a thermodynamic setting. Okay, so I'll just make that statement and stop here. So, are there any questions? No, yeah, I mean, yeah. When it's degeneracy, there are multiple global minima. Okay, I mean, well, yeah, that's a degeneracy. So, but here, I mean, here it is more. It makes more sense when they're unequal. Okay, it's not like they cannot go from one to the other, etc. I mean, even the other case, right? You can ask. Yeah, you're right. Yeah, there's a degeneracy. There, I would say there are two global minimum, but then I will not say that actually. I just say that there are two minimum. That's all. Okay. Yeah. Okay, so tunneling is a quantum concept. Okay, so but here, there are quantum fluctuations come into play. Okay, so tunneling is something if you have okay, so the quantum effect will take you from one minimum to another or one local. So in the metastable case, it will tend to go to the ground state. Okay, so but here the fluctuations are not quantum; they are thermal. That is the difference. Okay, so thermal fluctuations is what will. So if you wait long enough, thermal fluctuations will take it to its true minimum. But that may you may have to wait very long. Okay, those time scales. We are not doing dynamics here, right? We're doing equilibrium stuff. So we just have to say, eventually the metastable guy will go to this guy. End of story. No, that we have not discussed dynamics. We have nothing. We have no means of addressing that story here within our setup. But I'm sure it can be answered.